Howdy. So we're going to go over Newton's third law today. Newton's third law. So I'm going to be actually looking at my other screen. So it'll look like I'm not looking at you, which is kind of odd. Okay, so we got Newton's third law. And the first question is, what is Newton's third law? So I have a person here, and they're trying to walk. They're trying to accelerate themselves to the right. And in order to do so, they need to push backwards on the Earth. And so they're actually pushing backwards. They're not pushing themselves forward. They're pushing the Earth backwards. So Newton's third law, in Muggle speak, is action and reactions. For every action, there's an equal and opposite reaction, which is, in physics, it's not the greatest way to say it. So we're going to take it on and see what actually happens. The answer in physics speak is for every force, there's an equal but opposite force, and forces always come in pairs. And so what that means is when the person pushes backwards on the Earth, that's the force of the human on the Earth, there's an equal but opposite force in the opposite direction, which is the force of the Earth pushing on the human. So that's our first question, Newton's third law. What is Newton's third law? The second question has to do with this. It has to do with the acceleration of the Earth versus the acceleration of the person, since they're both experiencing a force. So the next question is, do they accelerate equal but opposite? And I think your answer would be no way, Jose. So it's the same force on the Earth as it is on the human, and yet the human obviously accelerates forward, but the Earth seemingly does not accelerate backwards, not even a tiny bit. Or is it a tiny bit? So the question becomes, why? If the forces are equal, then why or why not does the Earth not accelerate backwards at the same rate as the person accelerates forward? So why not? And the reason has to do with the masses. And the Earth is massive, and the person is not. And so that brings us to Newton's second law, which is the acceleration will be proportional to the net force, and the net force is the same, but it'll be inversely proportional to the mass, and the mass of the Earth is obviously much, much greater. So the human is going to accelerate noticeably, while the Earth is going to accelerate, but imperceivably small. So we got this picture, and the picture basically just says, in color, that the acceleration is in red. It's going to be way different, even more different than is shown here. But Newton's third law would say the force of B on A is the same as the force of A on B. In this case, the force of the Earth, the person on the Earth, is the same as the force of the Earth and the person. But the masses are so different that it makes the acceleration different. And so, in a nutshell, that's Newton's third law, but it's also Newton's second law, which has to do with how they accelerate. So here's kind of the wrap up of the notes. Newton's third law is action and reaction. The forces always come in pairs, and those forces are always equal and opposite. So you can just say the force of A on B is the same as equal and opposite the force of B on A. The force of the hammer on the nail is the same as the force of the nail on the hammer. So the reason they accelerate different is because usually the masses of the two objects are different. Now, if the masses of the two objects are exactly the same and all other things being equal, the acceleration would be equal, but that's not typical. Typically, the hammer is much larger than the nail. And so you have this picture which attempts to show proportions with the sizes of the letters. Okay, well, that brings us to our last part, which is to try to see if we can answer a question that has to do with Newton's third law leading to Newton's second law. So here I have Bronco the skydiver, and he's being pulled down toward the Earth. He's skydiving, and obviously the force of gravity is pulling him down, and so that would be the force of the Earth on Bronco. And so the question is, what is Newton's third law? Well, Newton's third law would say that the force of the Earth on Bronco is going to be the same as the force of Bronco on the Earth. So what the heck does that mean, right? The forces are always equal and opposite. So if I if I was to draw the force vector for Bronco on the Earth, it would be equal and opposite. And so this is true. This is Newton's third law. It always comes in pairs. And later on, we'll actually look at the specific equation for gravity. And you'll see that mathematically this is true. Now, the Earth has a greater mass than Bronco, but actually the force between them is the same. The force of gravity is the force pulling the two objects together. Okay, so from there, you have to say, well, what is the effect different? And so the effect brings us to Newton's second law. And as we said, the acceleration will be different because the mass is different. And so Newton's second law would tell us that the acceleration will be different because the two masses are also different. So in this case, I can once again revert back to that drawing and tell you how they accelerate. And so here is the acceleration of Bronco, and you can see that the A is large, and then here is the acceleration of the Earth, and the acceleration to Earth is small. And so when we put it all together, this is what it looks like, hopefully. One more step is that Newton's third law says that the forces that we have are equal and opposite. This force down is equal and opposite to this force up. This force here is going to be equal and opposite to this force down here. But the acceleration is vastly different because their masses are vastly different. And so the mass of Bronco being small gives us a relatively great acceleration, in this case 9.8 meters per second squared. And the mass of the Earth being large gives us a little teeny tiny imperceptible acceleration. And so there's quite a few videos online that talk about what would happen if everybody on the Earth jumped at one time. Can the mass of a human actually affect the acceleration of the Earth, which is an interesting question. Jeremy Avisos actually has a YouTube thing on that, and there's other people that have put that out as well. The question that you could Google would be, what would happen if everybody on the Earth, all approximately 8 billion people, were to jump at once? Would you feel it? Would it make an earthquake? Would the Earth accelerate away from the people? So anyways, that is Newton's third law, that for every force, there's an equal but opposite force. But that doesn't mean that the acceleration between the two will be the same because of Newton's second law. Okay, I hope that explains things, and I will talk to you later.